So, welcome once again to our discussion on panel data econometrics. And yesterday, we were learning about how to estimate a fixed effect model and how to interpret the coefficients, what are the different interpretations of 3R square measure, what we get after estimating a fixed effect model. And then we have also compared the fixed effect coefficients with LSDV, and then we said that what we observed, the coefficients are actually same in magnitude as well as in their standard error. But LSDV model is practically very difficult to implement when you have too many observations, right? Because it includes too many dummies in the model, right? But one thing we have not discussed about the R square measure in LSTV and fixed effect model, and that we would like to see today in our estimates. So, we are going to use the same data set which is basically the impact of labor or job market training on employees performance. So, this is XT set, once again XT set F code, and then F code, and then here. So, what we will do, we will first estimate the fixed effect model, which is XT reg. Then we have performance measured by L scrap, and then we have grant, and we have grant previous year, and then we will say that this is basically the fixed effect model that we are going to estimate. So, this is our fixed effect model we have estimated, and from this what you can observe that within R square, basically which is most relevant for the fixed effect model, because that explains what is the total percentage variation, time variation in Y, we can actually explain by time variation in X, that is mostly 17.34%. Now, the same model if we estimate by LSDV, sorry, this is once again so instead of xtreg, now we have to put reg command. So, this is basically regress, then L scrap, then grant, and one, and I dot F code. That is the command when you are using LSDB model, and here we are considering one way error component model. So, there is no time fixed effect. So, this is the LSDB model we have estimated, and now if you look at the R square of this LSDV, look at the R square is 92.51%, whereas in fixed effect model here it is only 17.34%. Now, if you look at the R square measured, that means LSDV gives almost 5 times higher R square than the fixed effect model. Does that mean an LSDB model is always preferred to fixed effect? First of all, why is the R square so high in LSDB model? Can you think of why the R square is so high in LSDV? So, this is the question I am asking. y the r square. So, this is Fe versus LSDV, and my question is, why is r square LSDV is so higher than as compared to r square Fe? Now, the answer is very simple, because in LSDV we are actually including too many explanatory variable in the form of too many dummies. So, obviously, when you include too many dummies, that means you are almost explaining the unobserved heterogeneity quite well by including too many individual specific dummies. That is the reason r square is too high in LSDV, right. So, there are too many explanatory variable, that is the reason there are too many explanatory variables in LSDV in the form of individual specific dummies. Individual specific dummies. As a result, we are able to explain a significant portion of YIT. Okay, that is the reason. But that does not mean that LSDV, but that does not mean LSDV is always preferred to Fe, because if you include too many explanatory variables, obviously you will be able to explain a larger variation in the dependent variable, but based on the r square we will never select Fe and LSDV. There should be a proper justification. When there are too many observations, we cannot actually apply LSDV because of the degrees of freedom problem, and it would be practically impossible to estimate sometimes. That is one thing I would like to mention upfront. Now, in the fixed effect model, when we write our equation is YIT equals to beta 1 XIT plus AI plus UIT. So, this is the model, and the assumption what we made that covariance between XIT and AI is actually not equals to 0 for Fe to be implemented. Now, suppose covariance between XIT and AI is actually 0. There is no correlation between the unobserved heterogeneity, individual specific time constant effect, and the explanatory variable. None of the explanatory variable is actually correlated with the unobserved effect. So, in that case, that fixed effect transformation is not applicable, because if we remove that, then what will happen? We are actually calling for some kind of inefficiency in our model. Okay. So, when that is not correlated, we need a specific form. So, when the next question is then, if our model is YIT equals to beta 1 XIT plus AI plus UIT and covariance between AI and UIT, covariance between AI and UIT is actually 0, then the first question that comes to our mind, should we work with a single cross section? We can actually work with a single cross section when the unobserved effect is actually not, sorry, here I made a mistake, here this is XIT. When the unobserved effect is actually not correlated with the explanatory variable, we can always work with a single cross section, because the main reason for using panel data, if you recall, I said that if you use more than one period's data, then actually we can eliminate AI by first difference or fixed effect transformation. Okay, that was our objective. So, we included AI in the model, and we have also accommodated the fact that this AI is actually correlated with your XIT. Now, if they are not correlated, then there is no need of panel data. We can actually work with a single cross section. But if we work with a single cross section, then what will happen? The other advantage of using panel data we cannot enjoy. And what is the other advantage? Other advantage is capturing multiple distributions for the dependent and independent variables. When you work with a cross section, you will be able to capture only a single cross section for both YIT and XIT. So, that is the reason. So, we can work with a single cross section in this context, but we will not be able to capture multiple distributions of YIT and XIT in cross-sectional data. So, we will not be able to enjoy the other benefits of panel data, right. So, because of that, we still need to work with panel data, but fixed effect and first difference transformation will not work. We need to have a different model known as random effect model. Random effect model. Okay. So, that means in random effect model, please keep in mind the main assumption is actually this, that the unobserved effect, individual specific time constant, unobserved heterogeneity is not correlated with the explanatory variable. That is the assumption. Now, random effect model we can get starting from a fixed effect model only. So, in fixed effect model, our equation is YIT equals to beta 1 XIT plus AI plus UIT. Now, what I will do? I will decompose this unobserved effect AI as beta 0 plus epsilon I. What is this beta 0? Beta 0 is actually the common unobserved effect okay, or I can say that this is average, and epsilon I is epsilon I. So, beta 0 is the average or common unobserved effect, and epsilon I is a random deviation from beta 0. So, if we think of AI is basically ability, which is the unobserved factor, beta 0 indicates what is the average ability in that sample, and epsilon I is basically a random deviation from that common ability factor. So, epsilon I is basically the ith individual's random deviation from the sample average ability factor. It can be positive or it can be negative. Okay. So, if we decompose AI into beta 0 and epsilon I, then our model would become YIT equals to beta 1 XIT, or I will first write the intercept beta 0 plus beta 1 XIT plus epsilon I plus UIT, right? And these together sometimes you can write VIT, composite error term, which is indicated by epsilon I and UIT. Okay. Now, we cannot estimate this model. So, that means this becomes beta 0 plus beta 1 XIT plus VIT. We cannot estimate this model. So, beta 1 XIT plus VIT. Now, when this AI, this epsilon I, and the assumption what we make here, covariance between epsilon I and XIT equals to 0. Now, in this model, can we apply pooled OLS? Can we apply pooled OLS? Since XIT is not correlated with epsilon I, can we apply pooled OLS? Now, pooled OLS is not applicable. Why? Because this epsilon I, we cannot apply pooled OLS as epsilon I will always be there in VIT for all t, and as a result of which VIT will be serially correlated, leading to autocorrelation. Okay. So, pooled OLS is not applicable. Pooled OLS is not applicable. This is the justification. Then what we will do? We will make a different type of transformation when our model is this. So, yit equals to beta 0 plus beta 1 xit plus vit equals to epsilon 0 plus uit. So, that is basically vit. So, what we will do, instead of removing the entire epsilon, this is epsilon I. Okay. Now, what we will do, we will use this transformation yit minus lambda yi bar equals to 1 minus lambda beta 0 plus beta 1 xit minus lambda xi bar plus vit minus lambda vit bar. And what is this lambda? How is this lambda defined? Lambda equals to 1 minus sigma square u divided by sigma square u plus t into sigma square epsilon to this. Okay, where sigma square u is basically variance of u and sigma square epsilon is basically variance of epsilon. Now, sigma, the question is then, to get this transformation we need to have sigma hat, we need to get sigma hat. Sigma, sorry, this is lambda. Lambda is always unknown, but can be estimated using sigma square u hat and sigma square epsilon hat from Fe or LSTV. So, the sigma square u, sigma square epsilon, they are all unknown population parameter, but once we estimate a model either using fixed effect or LSTB model, we can always get their sample counterpart, which is sigma square hat u and sigma square hat epsilon, and using this we will get lambda hat. So, this is the random effect transformation. This is called random effect transformation, RE transformation. Okay. That means, instead of removing the entire yi bar, what we are doing, this is called quasi time demeaning. This is called quasi time demeaning. Quasi time demeaning. Fixed effect transformation is called time demeaning because that was yit minus yi bar. Here we are removing only a fraction of yi bar, lambda fraction of yi bar, here also lambda fraction of xi bar. That is why instead of calling time demeaning, random effect transformation is called quasi time demeaning model, right. So, with this what we are doing, we are solving the autocorrelation problem, at the same time we are solving the autocorrelation problem that we were having in the model of pooled OLS. So, this transformation is known as, when we apply OLS in this transform model, that is called generalized least square. Okay. So, application of OLS, this is called GLS, which is nothing but application of OLS, in the transform model. And the transform model is basically this model, which is the quasi time domain, because this VIT minus lambda, this is VI bar. Lambda VI bar is basically free from the autocorrelation problem. Okay, free from the autocorrelation problem. That is how, when the unobserved effect is actually uncorrelated with the explanatory variable, instead of using pooled OLS or fixed effect transformation, what we do actually, we use the lambda transformation. That means a lambda fraction of YIT and XIT, sorry, YI bar and XI bar is removed from YIT and XIT. Okay. Now, this random effect model, if we look at very carefully, we can understand a random effect model is the more generalized version of pooled OLS and fixed effect model. We can prove that. For example, let us say two alternative cases. Case 1, let us assume that sigma square epsilon is tends to 0. That means, which implies insignificant unobserved effect. So, if sigma square epsilon tends to 0, from this lambda expression of lambda we can understand this becomes 0, then this become sigma square u divided by sigma square u square root, that also become 1. So, lambda will become, this will become lambda equals to 1 minus 1 equals to 0. So, if that is the case, if lambda is 0, then our model becomes YIT equals to beta 1 XIT plus VIT, okay, when lambda becomes 0, and this is nothing but pooled OLS, which is quite reasonable. That means, what does this transformation, what does this particular case indicate? If at all the unobserved heterogeneity is insignificant in our model, why should I go for fixed effect or random effect transformation? Because the entire idea behind using the fixed effect and random effect transformation was a significant presence of the unobserved effect AI. If that itself is insignificant, then we can very well apply the pooled OLS, because that was only creating problem. If you look at why pooled OLS was not applicable, because in this model this epsilon I will always be common in this VIT. So, if we apply pooled OLS, then VIT will be auto correlated, serially correlated. So, if that is not significant, then instead of using fixed effect or random effect transformation, what actually we should do, we can very well use a pooled OLS model. So, that means we can understand that pooled OLS is a specific case of this random effect transformation. When lambda equals to 0, we get pooled OLS. Similarly, case 2, when t, total number of time period, tends to, let us say, infinity, you have a large number of time periods, then what will happen? If that is the case, then lambda will become 1 minus, when t tends to infinity, this denominator t multiplied by sigma square e also become infinity, and sigma square u when it is added with infinity, that is also become infinite, and sigma square u divided by infinite, that becomes 0. So, 1 minus 0 equals to 1. Okay. When lambda equals to 1, this transformation becomes yit minus yi bar equals to beta 1 xit minus xi bar plus vit minus vi bar, which is nothing but fixed effect model. That means, with these two cases, what we can say that pooled OLS and fixed effect models are special cases of the random effect model, because both the models can be derived from the random effect model assuming a specific value of lambda. So, what we can say that both pooled OLS and FE are special cases of random effect model. That we have to understand. Okay. So, when lambda actually tends to 1, then random effect estimates will also tend to fixed effect estimates. When lambda equals to 0, we can understand that random effect estimates will tend to the pooled OLS. Now, what we will do, we will take one data set, another data set, and we will try to understand how to estimate a random effect model and their interpretation.